And even in lab, you're on this
2 8.
How do you feel about
Masterpiece. Steal that $, which would a different $.
It's okay.
Put it in the fridge.
It's good for us.
And actually, you probably finished chapter 10, starting chapter 11. 12 is another new material. Just kind of summarize what you've learned. So we're in pretty good shape.
Which one?
Oh, wait.
Do
Hold
you
on.
have any
Let me
questions?
get my phone.
About homework?
Is that homework?
About homework or about anything at all?
Anything, you know,
Yes, that's a good
financially?
question.
No.
Any other extra credit other
I leave
Um,
early, so.
The car wash is
Yeah, I'm kind of just
Saturday,
stole your
23rd. I'm not
book.
gonna have a sheet.
Oh, I don't know. Well, just, I leave early, so.
This new teacher just make sure to interrupt the entire class and be like, can I have my book?
Excuse
We
me.
have 3 time slots that are still kind of not full. I mean, they're full.
Oh, boy.
The first two time slots are ridiculously full. You know, we just have way too many people.
Oh, so then I don't have to come in
From
at
8:30
8.
to 10:30 and 9:30 to 11:30. We have probably 30 people in each of those slots. So, if you know, you won't be doing much anything, you shut down.
I'll do the 10.
Well, I'm gonna pass the sheet around.
Okay.
So if you wouldn't mind signing up for a 2-hour block, you know, great.
I need it back on the.
And I'll wait till the slackers to be
December 12th. Oh, it's
First
like,
final.
yeah, 10, 11, and 12.
Anybody member of Phi Theta Kappa here? Anybody Phi Theta Kappa member? You guys met at the meetings? No?
Oh, I'm not, I don't know the
Meeting. Anyway, the sponsor called me, left a message yesterday, they want to do a beach cleanup. So I'm going to tell them, yes, we'll tag along there, their beach cleanup. So that might be an extra good opportunity, usually on a Saturday, one of the local beaches. So I'll find out from her when she wants to have it, hopefully this semester. And that'll be another opportunity. And then Jensen Beach Elementary, I'm expecting to hear from them any day. Every year they call us to go judge their science fair, the kids' science fair.
I will do that.
So we'll see if they give us a call this year.
That's
We've done it for the last 8 or 9 years. And so that will be another extra credit opportunity, you know, as soon as I find out.
Be a joke.
And then there's always study. You can always just lock yourself in your room and study. And that, you extra credit that way too.
That's effort, though.
So I'll pass this
Dedication.
around in a few minutes.
I have like a hole in my pants.
So we'll have a test next week. I haven't made it up yet, so, but it's going to be based on the easy questions from homework. And things that I cover in class will be on the test. The only 2 mechanisms that you need to know is, I can remember their own stuff. Let's see, I think maybe there's more than 2 mechanisms. Anyway, make sure you know this mechanism, how to make an alkene from an alkyl halide. You want E2 mechanisms, that's what it is. It's a branding mechanism. So know the E1 and the E2 mechanism. Let's do the E2 with alkyl halides, that's the easiest one. X is a halogen. Okay, so I'll ask you for the E2 mechanism. Okay. So this is a single-step process. I'm looking for 3 hours. All occurs simultaneously in one step. Okay. So anytime I ask you for the mechanism, I'll give you stir material, I'll give you the product. If it's a brand name mechanism, I'll ask you, I'll give it to you. Sometimes they're not brand names. Anyway, so this base attacks the hydrogen, pulls over this hydrogen, this peroxide swings in, this swings out. Okay. So if we don't care with the other product to be X minus and HB. I don't care how you font, you know, first. Okay, usually you need a strong base to favor the E2 mechanism. Okay, so I'll put a note on that, because I'll use this to make up my test, to remind myself. Then, the E1 mechanism, usually you'll have a weak base that's not charged, and you end up with an alkene. And again, we don't care about this HX and base. And this would be the E1 mechanism. This occurs in 2 steps. And actually, you could also write, instead of these products, you might see HB plus and X minus. But then these two react afterwards to form this and this, but we don't really care about these guys, just how did you get that the organic product? So that would be E1 mechanism. First step is a slow step, it involves one substance, that's why it's called the E1. And so, first thing is, this is a weak base, it's not going to attack this hydrogen, it's not strong enough, so wait for this to leave. So this is a multi-step process unlike the E2 mechanism, which occurs in a series of steps. And then in the second step, you can have your base attack this in here, and that gives you your product. Okay? So it's not too bad. Now, X stands for halogen, using in organic chemistry, and halogens are covalent groups. They don't have to be consistent when they leave. But if your leaving group is OH, then you're going to have to add an acid to make that OH better leave. So this is also an elimination reaction. It doesn't have a name associated with it, but make sure you know this mechanism, both these mechanisms. Okay. Instead of X being a halogen, let's make this leaving group an OH. Okay. And usually if it's an OH, then the reaction is done in acidic medium. And you can have water present. Anyway, you get this, and you get water. Okay, so in this case, OH is evaluated because at first you have a proton transfer, and that gives you a better leaving group. Okay, then some base, say water. Can attack this swings in here, and this leaves. And so you get your product. So it's like the E2 mechanism, except it's an extra step. See, the base, this can't be charged. This can't be hydroxide. You can't have a negatively charged base. If you get a hydrogen there, that's going to protonate the negatively charged base. So don't write B minus or OH minus. You can't have that. But anyway, the extra step is first protonate this. Now it's like a E2 mechanism. The base comes in, you just have to be neutral. Close this continuously, all in one step. So the second step, you have 3 hours. First step is protonation. So that doesn't have a particular name. They don't call it the E2 mechanism, but it's like the E2 mechanism. Okay. And then the messiest of them all is similar. First step is identical. don't really care about the other five, it's just how is this formed. Okay, so again, OH is a bad leaving group, so it's the first get proteinated, just like the last case. Okay, so everything's the same so far. Okay, now, in the next step, this just leaves. Okay, and so you form a carbocation. And then in the last step, let's rewrite water. Remember, we have water over here. On the next last step, propane cis. No, it doesn't. What am I thinking? You take substitution. That would be if substitution is mixed. This is elimination. So the water takes this moves in here, and you get your final product. All right, whatever it is. So that's 3 steps. First step is proton transfer. The proton gets transferred from here to here. The last step is proton transfer. The proton gets transferred from here to here. Okay, and so proton transfer, good leaving group, this leaves carbocation, this affects this is going to be gets off. So those for the chapter on alkenes, preparation of alkenes, those 4 mechanisms, just to make sure you know for that check. It doesn't have a brand name. It's like an E1 because it is elimination, and the slow step involves just this guy right here. Actually, this guy right here, going from here to here. Anytime you form a carbocation, that will be the slow step. Okay, so this is like an E1 mechanism. Because you do form a carbocation. So this you get a protein. If this is a halogen, it just leaves. So imagine this is X. This is X, you don't need that. It just leaves. You form your carbocation and the base pulls off the hydrogen. But if you have OH, then you have that initial beginning step where you have to protonate the OH to make it better. All right, so those are the, I'm not giving you all 4 mechanisms, 2 or 3 if we're on the test in that chapter. Okay, and then the next chapter on the reaction of alkenes, I think I'll probably just have one mechanism for that. Here they are. I'll put them down now, so I'll have this sheet of paper to go by when I make a test. So this is formation of alkenes, it's elimination. Now alkenes react by addition, and this is the easiest one. HF, let's use HBr with that. Okay. Okay, so definitely you see that. And so how do you go from one to the other? This would be a potential mechanism. I don't know. Let's write this down over here. This is my pivot point right here. So imagine this is the windshield wiper, and I'm going to swing this down at this point here. Okay. So first step is 2 arrows. Now this pair of electrons here swung down and tapped the H. And this left, you get Br minus. Notice we formed a more stable carbocation. See? So the carbon had the most hydrogens, not the hydrogen. The other carbon doesn't. It gets a positive charge. This is the secondary carbocation, more stable than the first carbocation. And in the second step, this just attacks this to give you your additional product. Okay, so this occurs in 2 steps. 2 arrows in the first step, 1 arrow in the second step. And the only other one, this is number 5. Now these mechanisms, they show you in the book, but lots of times they don't ask for these in the homework because they already show it to you in the book. You want to make sure you know how to do these mechanisms, okay? Chemists love mechanisms. Anyway, here is another one. Chew on. Water is not strong. See, HCl is a strong enough acid. If you want to add water, water is not strong enough of an acid, so you're going to have to add H plus. And then you're going to get the same kind of thing. The carbon is most hydrogens. The one on the right gets the hydrogen. And the other carbon, the one on the left, gets the OH. Okay, so that's the... Now, just like before, the first step over here is protonation. This is electron rich. This is a nucleophile. It's got a lot of electrons. It wants a nucleus. So same thing here. It just said HBr's acidic enough to supply a hydrogen. Water's not. So we have to use sulfuric acid that supplies H plus. So the first step is just like up here to H plus. Here's my pivot point right here. Going to sweeten down to form the more stable carbocation. And just like this before, the second step is the nucleophile is going to attack. But here we can't have a negative charge nucleophile. This is an acidic medium. See, so up top we have a negative charge nucleophile attack. Here we just have a water attack. And after water attacks, then you're essentially home free. So now you can be lazy, that's how chemists do it. And just, these pair of electrons go back onto the oxygen, you will see minus H plus. So if you have to add an acid as a catalyst, the first step is a protonation, the last step, deprotonation. The first step, you protonate this, proton transfer from this guy to here. And the last step is proton transfer from here back. So this is catalyzed by the acid, because you need an H plus in the first step, and you lose an H plus in the last step. Okay. So those are the two mechanisms in the chapter on reactions of alkenes. And I'll draw simple structures, not complicated structures.
Do we need to know anything about the major and minor products for the test?
I'm usually going to ask you for the major product.
And that would be the big portion of the negative H plus, correct?
Yeah.
Okay.
And in this case, if I ask you for the mechanism, I will always give you the starting material, the reagent, and the product. So you know what your reaction is. And I'm going to ask you, how did you get the product? So I'll ask you for the major product.
Okay, could you do one problem for me?
Sure.
Chapter 8,
Yeah.
on page 353, 8.15. Any of them?
What number was it?
Page 353, 8.15, any of those, just so I
Okay.
can see.
I think that relates to a question that you had also. Save these guys. There's a lot of fine points in organic chemistry that you can just go insane if you had to memorize all the fine points. That's why they invented advanced organic chemistry. So if you think that, then you will get into a lot of fine points. So typically, if you form a double bond, the more highly substituted alkene is going to form. So that's what you're going to see in the test. That's the more stable product. But you can manipulate the situation so that less highly substituted alkene is formed. Now remember stabilities. This type of alkene is the least stable. You don't have any R groups. You have 4 hydrogens. Okay. This is the most stable alkene. You have no hydrogens attached to the carbons and double bonded. So the more R groups you have, the more stable it is. Another way of saying it, the more H's you have, the less stable it is. So typically, if you have an issue, let's do this. Let's see what we have. We have methyl group, CH3. Chlorine. Let's change this, doctor this up a little bit. Let's put a hydrogen here. Let's put a methyl here. Some doctor and I'm going again. Okay, so anytime you do a dehydrohalogenation, it's always this. First of all, carbons have to be right next to each other. You can't have dehydrohalogenation between these two carbons here. You gotta be next to each other. One has to have a hydrogen. One has to have a leaving group, either a halogen or an OH. Okay, so you need to know about. So do you see this let's see if I want to do this. Yeah, there's three potential products you can get. Let's put some of these hydrogens in here. Okay, there's three. Now this carbon has a halogen. That's going to lose the halogen. Okay, but do you see that the base can pull off this hydrogen, give you a double bond here, pull off this hydrogen, give you a double bond here, or pull off this hydrogen, give you a double bond here. So there's three potential products that you can get if you use a typical base. Okay, and usually they use a small base. Okay, like sodium hydroxide, so hydroxide ion, or the methoxide ion. These are small bases. That's what you will see. But anyway, you could potentially get this chlorine and this hydrogen. You can get a double bond here. Oops, that's the way I read it. Hydrogen CH3. That's one product. I lost this chlorine, this hydrogen. I could lose this chlorine and this hydrogen. See, so another potential product. Look at this. I'll get lazy, so it's CH3. But there's a third potential product. You could lose this chlorine and this hydrogen here. In which case, so, if you start with that material on the far left and you do dehydrogenation, I'm going to probably just ask you for the major product. And so look for the carbon that has the most, you don't want the carbon that has the most orbitals or fewer hydrogens. See, this double bonded carbon has 1 or 2 orbitals and 2 hydrogens. This has 1, 2, 3 orbitals and 1 hydrogen. So I know this is more stable than this. And this is no hydrogen. So these three, this is the most stable, and this is the least stable. So I would ask you just for the major product. That would be the one at the far right. Now, are you stuck with this? And the answer is no. Here's the final one. And I talked about this, but I'm not going to quiz you on this, but it's nice to know. The base has to get in here, get in here and get this hydrogen, get this hydrogen, get this hydrogen. If the base is huge, it's not going to be able to get in there very well. It's going to stay in the outskirts. So if I use a huge base, it won't be able to get into this position here or this position here. It can get in this position easier because this is kind of on the outskirts. Okay. Let's take another example. Let's take this. Let's put a chlorine here, and a hydrogen here, and a hydrogen here. Now you know typically the double bond is getting up here. The base pulls this up. But if you have a huge base that can't get in here, it's going to stay in the outskirts. So if your base is very, very, very large, you're going to get the unexpected product. It's not going to get in here very well. It's going to stay in the outskirts and put the double bond here. So that's a fine. So normal bases like this give you the expected product. But if I, instead of using this base, if I use this base, if I use a TP-toxide line, this is a huge base. Well, it can't really get in here as well, or in here as well. This is more the outer fringes. See, here it has attacked a ring, it has attacked a carbon in the ring, or the hydrogen in the ring. The hydrogen. Here it's outside the ring. See, so this is hard to get to. This is easier. It's off the ring, off to the side. So if I use this base, it's going to pluck this off, and this would be my major product. Okay. So we won't worry too much about that, but you can manipulate the situation sometimes to get the other product. But typically, this is what you get. In most cases, you're going to get the more highly substituted alkene. But you have unusual circumstances like a big bulky base, then you get the less highly substituted alkene. So we'll stay away from those 5 ones. Okay? So I think in the book that you mentioned that, maybe the homework question will say we're using TP-toxide, and that's what they're saying. You might not get the expected product if you use a big bulky base.
So you're not going to put down a test where it has like the, TP-toxide?
I won't use that one, because you're still going to get some of this till you get a mess. Okay, so I'm going to use the smaller bases, and I'm going to see they kind of tricky look on that. See question D. You have a hydrogen here, and then pick one of these two and take it away. Let's take the hydrogen here. See? So the more stable product would be the double bond forming right here in the interior. The less stable product would be the double bond forming here. So typically, if you had a base, the base is going to pick on this hydrogen, get a double bond here. But if you got a big, bulky TP-toxide base, it can't get in here. It stays on the outskirts, fluxes. And so you get a fair amount of alkene here. So we're not going. You won't see that situation because it's just too messy. Instead, you can see the classic one. We use small bases like hydroxide or ethoxide or methoxide. That will give you the more highly substituted alkene. So if you use this, the double bond is here. Here it doesn't matter. Put a double bond here, here, here. It's the same compound. This top case here. So there's no hydrogens here, don't be fooled. You can't form a double bond here. There's no hydrogens. See, this carbon has 4 other carbons attached to it. You gotta have a carbon with a hydrogen. I'm sorry, a carbon with a halogen, and next door to it a carbon with a hydrogen. So this has a hydrogen, this carbon has hydrogen. So you can't get a double bond here, otherwise you have 5 bonds. You can't get a double bond here or here. This is a small base, the double bonds here. Okay. So I'm going to give you typical classic small bases, but you can sometimes manipulate the situation. Okay. So that's a fine point that you took another organic chemistry class, they start getting into the fine points. But on this PCATs or MCATs or dental cats, hopefully they won't give you the 5 points. They're usually the more straightforward, common organic chemistry questions. Okay. So this book kind of, all authors kind of mix it up a little bit. They don't want you to think it's always going to be this way. And it's usually one way, but then they tell you chemists can change the game so that they make it, the minor product can become the major product if you manipulate the situation. But we're not going to try to manipulate the situation. We're going to take the common garden variety chemical reactions and you form an alkene. Typically, the more highly substituted alkene is the one that's going to be favored. We should do some funny business.
Are you going to ask any questions about like rotating the
Well, if it's a ring, if you see a ring, then yes, then you got to worry. Then you need to worry about which directions the space or things are pointing. If it's a straight chain compound, nah, it's not going to matter because you have free rotation anyway. I'm not going to ask you for R and S. Okay? So if you see a ring, then it will be then you want to look closely and make sure that you follow the correct skill. So basically with the ring, if you do an addition reaction to a ring, you start with the carbon-carbon double bond in a ring. There's a bunch of different reactions, you gotta look these over, and you add X, Y. Remember, there's two ways you can add. X and Y can be pointed in the same direction, both up or both down, that would be syn addition. Or X and Y can be pointed in opposite directions. That would be anti-addition. So there are certain reactions you want to learn, which ones add syn, which ones add anti, for your long list. And then when you, there's only one case when you form a double bond, there's only one problem you got to worry about when you're forming a double bond. If you form a double bond by the E2 mechanism, use a strong base, and you get elimination. Remember, this is the only restriction you got to worry about in the chapter on preparations of alkenes. The groups that leave for the E2 mechanism have to be pointing in opposite directions. See? So bromine's going to leave, and hydrogen's going to leave, but this is the only hydrogen that can leave. This one can't leave. They're both pointing in the same direction. So you have to have what's called, anti-coplanar. They all have to be the same plane, and point in opposite directions. So only with preparations of alkenes, this is the only one you got to worry about, orientation. So the double bond will just leave. We get the double bond in this location. That's the only one you got to worry about for that chapter. The other chapter where you add across carbon-carbon double bonds, there's a lot of different ones. Some of these reactions you learn only add anti, some only add syn, and some add both. Okay? If it's a carbon-cation mechanism, it doesn't matter. You get syn and anti-addition. If it's not a carbon-cation mechanism, then you typically will get either syn or anti-addition. Okay, and for this test, most of the reactions, I give you the starting material, I give you the reagent, and give you the product. Okay, and there's one set of reactions that will be different. We talked about this already. It's not a synthetically useful reaction. It's used to do structure determination, and that is you add ozone to a compound that contains a carbon-carbon double bond, followed by dimethyl sulfide. You're going to get any carbon-carbon double bonds you have become carbon oxygen double bonds. Okay? So you break the molecule into pieces. Okay? Let's see if I can get fancy here. I'm not going to get this crazy one, okay, so don't be upset. So just for fun. I wouldn't do this to you. But what did you start with? There's a couple possibilities. It's actually, no, actually not. It's only one possibility. Can you work backwards for this? And remember, when you had ozone followed by dimethyl sulfide. Any carbon-carbon double bonds you have in a molecule get snipped and they become separated as carbon-oxygen double bonds. I'll give you a hint. If you have carbon-oxygen double bonds at either end of a chain, then connect those two ends together. That was one time on 3 here. That's what it was. So you see 2 carbons at the end, 2 carbon-oxygen double bonds at the end of the chain. You know they were at one time connected, so just connect them together. And any other carbon-oxygen double bonds you see were also at one time connected. So can you work backwards, give you the structure of the starting material? If you did this ozonolysis reaction, you got these 2 pieces, these 2 smaller pieces, what would be the original structure? Notice we have what, 1, 2, 3, 4, 5 carbons. So that's 5. And this was at one time attached to another carbon double bond, so that's what these see. So this is what I started with, and ozone, this would be snipped up. I would get this chain right here. But I also had this piece and this piece here, so there must have been another carbon-oxygen double bond. Let's see, this count from here, 1, 2. So the second carbon in from the double bond. So 1, 2. This one, 4, 1, 2. From this guy, 1, 2, 3, 4. So from this guy, 1, 2, 3, 4. So this carbon right here, or this carbon here, or this carbon here, same thing, take your pick, either one of these, was at one time this. So if that were your products, working backwards, you would say this is the structure of the starting. This breaks off, that gives you this. This breaks off, that gives you this piece here. Then the second carbon from the double bond. So you can put this here, or you can put it here. Okay. All right, I won't be that nasty. But anyway, that's really one which you will have to figure out the starting material, because that's what chemists do. That's how they operate. Okay, so they find some new street drug, turn it into the crime lab. What the heck is it? Well, it can bubble ozone and BMS, break it into smaller pieces, and kind of work backwards. It's easier to study these smaller pieces than the big giant ones. They try to work backwards and figure out what the original structure was. All right. Comments, questions? Of course, there'll be naming compounds. I ask you about naming organic compounds. And there'll be one question. I don't think this is in the book, so write this down. It might be. I can't remember. I'm going to ask you to draw all the possible alkenes that have a particular form. Okay. So, and I'll tell you how many there are. There won't be a big number, but can you draw all the possible alkenes with carbon-carbon double bonds that have the form of, I'm going to get carried away here, C4, how many different ways can you put this? Now, here's the trick. You see how many different carbon backbones you come up with? 4 carbon backbones. How many different ways can you just arrange 4 carbons to form different backbones? So, of course, one way is this. Okay? And then the other way would be this. If you have 4 carbons, those are the only 2 backbones you can come up with. Anything else you draw is some repeat, it's already there. So 4 carbons gives you 2 possible ways. And then ask yourself for the first structure, how many different places can I put a double bond? Well, I could have put a double bond this end or the other end, it's the same molecule. Or I think you can see you can put a double bond in the middle. So those are 3 ways. And then this guy, you see, I have to rewrite this, just rewrite this as select. These bonds are not 90 degrees, they're not 180 degrees. How can we draw this a little bit different? Same thing, okay? But it doesn't matter if they're one left, right, or bottom, it's the same thing, okay? So, and then hydrogen, just fill in the blanks. Don't even bond the hydrogens, you know. If you put enough hydrogens on each of these carbons, so it has 4 bonds, you get enough using 8 hydrogens. So C4H8, that alkene has 3 possible isomers. And in fact, there's actually another one, which I may actually do. Include cis-trans isomers. Can any of these 3 exist as a cis and a trans? Remember, to be cis-trans, both the carbons have to have different groups on them. Both double bond carbons, they both have to have different groups. If one of them has the same group on the same carbon, you can't have a cis-trans isomer. So this last one is out for 2 reasons. This carbon has a methyl group and a methyl group. They're the same. So but it also has this. So either one of these would say this cannot exist as cis-trans. This carbon has a hydrogen and a hydrogen. That's the same group. It cannot exist as a cis-trans. But you see how this carbon has a hydrogen and a methyl group. Those are different. And this carbon has a hydrogen and a methyl group. Those are different. So this, if I asked you to include cis-trans isomers, I would ask you for 4 structures. I would say, give me the 4 structures that have alkenes that have the formula C4H8. Include cis-trans isomers. Okay. So the top one can exist and does exist. Let's draw it out. Cis isomer, you might draw it like this. And the trans isomer, you might draw it like this. I'm not sure how much they emphasize this in the book. Most textbooks emphasize it quite a lot. I don't think the author does very much, but anyway, I'm going to ask you to do, and it's not going to be a ridiculous number, okay? It'll be 3 or 4 or 5 structures I'll ask you to draw, and I'll tell you how many there are, so you don't give me 20. So be able to draw all possible answers. Now, I'm not going to ask you just for cyclic compounds. Cyclic compounds have the formula. Cyclic alkanes have this formula. So I'm going to say alkenes, because we're covering alkenes. Okay, so this would work. This would work. Both of these compounds have the formula C4H8. But they're not out, they're cyclic compounds. So I don't want those. Just the alkenes. These are cycloalkanes. So go cyclo. Don't go cyclo, I should say. Just give me here. All right, so naming. Stability, make sure you know stability. Here, group of alkenes, tell me which is the most stable, the least stable. Be able to draw isomers. I'll tell you how many there are. Be able to do cis and trans isomers. Mechanisms, there were 6 mechanisms we went over. There'll probably be 3 of those 6 on there. Reactions. I'll give you a starter 2, I'll give you the reagents, you give me the products. If you see a ring, then I'm interested in directions and spaces of the point. Don't forget McCall-McCall and anti-McCall-McCall orientation. And then 1 or 2 questions, I'll give you ozonolysis reaction. I'll ask you to give me the structure of the starting material. And I can't think of anything else. I might ask you about polarities. I don't know whether or not it's in the book. The more symmetrical molecule it is, actually, let's take these guys. Symmetrical molecules tend to be nonpolar, they tend to have low boiling points, And unsymmetrical molecules tend to be slightly polar, they have higher boiling points. So this is a perfect symmetrical molecule. These are right across from each other, these are across from each other. This will have a slightly lower boiling point, it's less polar. This is distorted, they got a pull here and a pull here, but no counterbalance here and down south. So this is slightly more polar molecule. Its boiling point will be slightly higher. So just remember, in symmetry, symmetrical molecules tend to be non-polar, and they tend to have lower boiling points. And molecules that are not symmetrical tend to be slightly polar, and they tend to have slightly higher boiling points. Let me see if they mention that. I don't know, I don't see it. But anyway, just be aware of that. If I find it in the homework, I'll ask it. If not, then I may not. I don't see it. Looks like we're off the hook. It's hard to include everything. Okay, the other thing I just realized, factors that favor E1 mechanism, factors that favor E2 mechanism. Okay, you should know that. Remember this, way back in chapter 8, page 375. I'm going to probably tell you, I'm looking for the substitution product or elimination product. This should test the elimination product. If you see these guys, you get substitution. Okay? You won't see that. If you see these, if you see oxygen as the base or nucleophile, then you can get either substitution or elimination. If it's a negative charge, you tend to get SN2 mechanism or E2 mechanism. See, powerful bases favor SN2 and E2. Weak bases, like these guys that are neutral, they tend to go by the SN1 mechanism and E1 mechanism. Okay? So just know what, if the attacking base is negatively charged, it tends to go by the E2 mechanism. The neutral tends to go by the E1 mechanism. And also, remember the reactivity. I can't go into every little detail. But remember the reactivity. E1 and E2 follow the same trend for reactivity. And somewhere, I'm sure they summarize this. It should be in your notes. We won't go into rationalization, we already did this, but just remember this, for this test. The E1 mechanism and the E2 mechanism are favored by the same factors, so that if the R leaving group, let's do it this way, the leaving group is attached to a third-degree carbon, that reacts faster than if the leaving group is attached to a second-degree carbon. This is both E1 and E2, okay? And if the leaving group is attached to a primary carbon, it goes the slowest. Second degree carbon. Okay, so just remember that reactivity. So if I give you a series of alcohols where the leaving group is OH, or alkyl halides where the leaving group is halogen, I say which one reacts the fastest by E1 or the E2? The third degree. Which one reacts slowest? First degree. Okay, so we talked about that. There's different reasons why this is so, and you can over your notes and reading. Just make sure you know those factors. Third degree DB groups react faster by the E1, E2 mechanism. The bases, negatively charged, the E2 mechanism is favored. The base is neutral, the E1 mechanism. So make sure you know those factors. This is in chapter 8. All right. That's enough. I can't find a question on polarity and boiling points, so we're off. Anybody have any comments or questions? Sick of this, huh? Okay. All right, let's move on to something else. Let's get you tired of something else. Let's talk about alkynes. We talked about how to name alkynes last time, so you're experts at naming alkynes. Just as a quick review, you have 5 carbons. You have an alkane. You have no double bonds, triple bonds. All these guys have any of A and E, so this would be pentane. And the all have uniformly CN, H2N plus 2. On the other hand, if you have a straight chain compound that has a double bond in it, then it's called an alkene. And so it has a general formula CN, H2N. And this would be a pentene. So get rid of the A and add E and E. And double bond is the lowest possible number since it's 2 pentene. So everything you learn about naming alkenes, extend that now to alkynes. You have a compound that contains a carbon-carbon triple bond, then it's called an alkyne. And has a general formula CN, H2N minus 2, and you need a number in many cases. Where is that alkyne located? And it's H2. So alkanes have any A in E, alkenes E in E, and alkynes Y in E. But everything you learn about naming alkenes and double bond, apply that to alkynes. Give the alkyne the lowest possible number. Okay? So that's not that big a stretch. They show you some important alkynes in this chapter that occur naturally, and some pharmaceutical ones too. Okay? Alkynes are much more expensive, much harder to get than alkenes. Okay? But, you know. All right, so let's talk about how do you make alkynes and what kind of chemical reactions do they undergo. There's not a whole lot of chemistry here. To make an alkene, you have to do an elimination reaction. Right? You learned this. That if you have X is a halogen, either by the E1 or the E2 mechanism, you can make an alkene. Well, you have to add a base, either neutral or charged. Anyway, if you want to make an alkyne, you need to do a double elimination. So you start with this and add a base, and it has to be a strong base. Weak base won't cut it. Okay? And you can do a double dehydrogenation. Okay? And you can have both halogens on the same carbon, or you can have one halogen on one carbon, one on the other. Doesn't matter. Okay, so that's the easiest way to make an alkyne. Do a double dehydrogenation. Now, with this guys, the base can be hydroxide, the base can be OCH3, it can be OCH2, CH3. And want to get fancy, we won't. We use butoxide ion. These bases are sufficient to pull off a hydrogen and a halogen. Oops, sorry. That happened. Okay, unfortunately, these bases aren't strong enough to pull off two hydrogens and two halogens. So the base has to be a powerful base. The base should usually be these amide ion, NH2 minus and Na plus. So sodium amide is usually used, or sodium hydride. Take your pick. That's the basis of choice. Those are powerful enough bases to pull off two hydrogens and two halogens. Okay, so it's like a double dehydrogenation. Now, don't worry about the mechanism. It's messy. The first step is the expected step. If you had, say, amide ion, this will pull off this hydrogen, this swings in here, this leaves, and you get, initially, you get this. Okay? Then you need a second, you need 2 moles of this. The second mole of this pulls off a second hydrogen and halogen. And actually, it's not that messy. You get that, okay? I'm not going to ask you that mechanism. It's just a double dehydrogenation. Okay, so from what you learned about stability of alkenes, compounds containing carbon-carbon double bonds, what do you think would happen if I gave you this? We add either sodium amide, NaNH2, or sodium hydride. So we do a double dehydrogenation. You see we have a choice as to where the triple bond is going to go. So try to make it in the interior. Let's pull off these guys, these guys. That tends to be a bit more stable. Okay, right at the end. Okay, so this is the only convenient way to make alkynes. Now we're getting to the rate. In Chapter 12, I mentioned just a review. Chapter 12, it kind of makes you do organic synthesis in a stepwise fashion. Okay? Because usually you don't do a one reaction to get the product. Usually you do a series of steps. So here's what Chapter 12 is going to be dealing with. So basically, just like mathematics, you're expected to remember everything you learned from the beginning. You're at a higher level math, they expect you to remember everything. So chapter 12 basically is multi-step synthesis. They just take all the reactions you've learned in the first 11 chapters and they start stringing them together. Because usually you don't get a product by doing a single step reaction, usually multi-step. Alkenes are dirt cheap. They're easy to make, to start with. Alkynes are expensive, cheap. So we're starting with an alkene, and we want to make, we do 2 steps. So what do you get with the first step? Okay, and then next thing, remember that. And then what do you get with the second step? See, so this is a multi-step synthesis. And since we're talking about alkynes, you know, hint is we're talking about get an alkyne. So after the first step, you're going to get this, right? You get bromine. And then you get your hydrogen water and bromine. Then in the second step, you get a strong base, you get double dehydrogenation. So that's what chapter 12 is all about, doing multi-step synthesis. Learning, putting together everything you learned in earlier chapters, and stringing these reactions together to get the final product. Matter of fact, the cheapest, most readily available compounds that chemists have are alcohols. Alcohols are everywhere in nature, and they're easy to start with. So actually, alkenes are more expensive. What they would actually start with is isopropyl alcohol, and you add an acid and heat it in the first step. Then in the second step, they add bromine. Then in the third step, they add sodium ethanol. Probably the most common reaction you'll see in organic chemistry is add an acid to an alcohol and heat it. That's what you did in the lab. You took cyclohexanol, methyl cyclohexanol, you add an acid and heat it. And after the first step, you're going to get dehydration, right? You bromate this OH, it leaves, you get a carbocation, this switches the heating and so on. Then, after the second step, you get this. And then finally, to the third step, the final product, you get tryptophan. So most organic synthesis begins with alcohols. And so again, this is a preview. Chapter 12 is nothing new. They just kind of start stringing these reactions together. Just give you some examples of what you want me to do. So that's why organic chemistry is such a pain so hard. You've got to remember all these little reactions from day one to do multi-step organic synthesis. So anyway, this is the only easy way to make an alkene. The final step is do a double dehydrohalogenation. That's kind of nice. This is only one way to make an alkene. All right, what kind of chemical reactions do alkenes undergo? Well, we're going to talk about that. What kind of chemical reactions do alkynes undergo? They undergo addition reactions. Okay, with a few little special twists, of course. But for the most part, alkynes, compounds containing carbon-carbon triple bonds, undergo the same kind of reactions as alkenes. It's just that you need to add 2 moments. Okay. So here you get, X and Y. Here you get 2 X's and 2 Y's. Okay. So that's, with a few twists, that's about it. Okay. And the Kolmogorov rule applies. If you're adding H nucleophile, if that's what you're adding, then typically the carbon has the most hydrogens, gets the hydrogen, and the other carbon gets the other group. So that's where it's the same as before. I have extra pencil. Thank you. All right, so let's do the stuff that's the same. Then we'll do something that's kind of weird. Okay. What's the same? If you add HCl, HBr, HI, remember we did that? Remember we talked about adding HCl, HBr, HI, HCN, HOH, HOR. These guys are the same. have this. And you add 2 moles of HBr, HI, HCN, whatever, let's take HBr. I'm not going to say 2 moles, I'm going to say HBr. It's assumed you have a large excess. Okay, so what is the product? The mechanism is somewhat, but not exactly similar. They don't give you the whole mechanism, it's kind of messy. So we won't worry about the mechanism. There's no mechanism to worry about in this chapter. Okay. So do you see, hopefully, that the carbon has the most hydrogens? This one gets the 2 hydrogens, and the other carbon gets the 2 hydrogens. So that's kind of nice. Very similar to what you learned before. Now it works with HCl, HBr, HI, HCN. Does it work with H2O or HOR? Okay, but for now, we'll work with that later. Then the other type of reactions you saw was 2 halogens, X2, or X2 could be CO2, Br2, or I2. So you get the same situation here. You don't need to worry about who gets the groups because, you know, they're both the same. So we just add an excess of, say, chlorine, so you just write products. Okay, so that's kind of straightforward. And you also learn you can add hydrogen gas, HH, right? Hydrogen gas in the catalyst. So same thing as here. If you have an alkyne and you add hydrogen gas and a catalyst, you get an alkene. Now the nice thing about alkynes, you won't usually find them in a ring. I'm not sure we talked about that, why that's so. This is not particularly stable. This carbon is, what's the hybridization of these triple bonded carbons? sp3, sp2, or sp? sp, because this carbon has 2 single bonds. Okay, no lone pairs. So how many sp? That angle should be 180 degrees. That's linear, see? So when you have carbon-carbon triple bonds, the angle should be 180 degrees. If it's in a ring, you got a lot of angle strength. So you have some in rings, but they're not that common. So most of the time, if I give you an alkyne, it's going to be a straight chain alkyne. So when you add, you're not going to worry about which direction the base is going. All right, so anyway, those are the similarities. And there are some differences, of course. The differences are if you add water, you can't add 2 moles of water to this. Before you add that second mole, something happens. If you try to add an alcohol, you can only add 1 mole of alcohol. Before you add that second mole, something else happens. So that's 2 important differences. All these are the same, these are the same. Can you add just 1 mole of hydrogen? Yes. There's special ways you can do to just add 1 mole of hydrogen. Okay? And so we'll talk about that. And then remember, you can, this is called an oxidation reaction. You can take this, add ozone, followed by dimethyl sulfide. And this turns into this. What about if you have a carbon-carbon triple bond? You can add ozone, and I'm not sure what else, if anything, I think some water in the second step, but this turns into this. me double check what other step is. It might just be water or water in a vase. I can't recall, to be honest with you. Let me cheat. Yep, just water. Okay, so we're going to talk about several reactions when we come back. We'll talk about adding this and this across the triple bonds. That's the exception to the general rule that you can add 2 moles. We'll talk about this reaction. It's pretty straightforward. And then we'll talk about special ways to add 1 mole, not 2 moles, just 1 mole of hydrogen across the carbon-carbon bond. Okay. And then we'll be finished with this chapter. It's not that, it's a short chapter. And then I say the next chapter is short too. So I'm going to take a break. You can books here. Come on back.